Hi, we are the Winona Lunar Scouts, and this is our final presentation for the GLEAM Lunar Robotics Challenge.
Hi, I'm Stephen Shaw, and the team technical lead and oversaw the development of the electrical subsystems. To begin the project, we created a vision to share with the team. After creating this vision, we broke off and did some preliminary research, coming back together and presenting it to the team. We researched on things like LED options and camera options, as shown on this slide. Finally, we created a Gantt chart to help guide us in due dates and a general project development sequence.
Hi, I'm Maureen Pellicero, team lead and sensors expert for the Winona Lunar Scouts. We also divided the work of our PDR by specialization. This, as well as Stephen and my exposure to technical writing, helped guide us to success. We are quite proud of this document. Because our oral presentation was created well in advance, we had plenty of time to practice.
Hi, I'm Martin Amara, and I focused on network communication for the Winona Lunar Scouts. Going into mission day, we felt very confident in the mechanical performance of the rover. We had thoroughly tested the capabilities traversing ramps and flat surfaces. We knew the battery would provide a minimum of 3 hours of exploration time. We had developed a Python visualization script that would update in real time to observe data as we explored. Also, we were aware of some weaknesses. The servo motors, which control the pan and tilt our camera, IR camera, and the LiDAR, were inaccurate. In the days leading up to the drive-off, we made several changes to our code. We did not have time to sufficiently test these changes. A website was developed too late and could not be used. The team also realized the lag in the video was a huge obstacle to our success. We had addressed the problem. We could have explored the course quicker and more efficiently.
Hi, I'm Morgan Mum, and I focused on mechanical design for the GLEAM Lunar Robotics Challenge. Upon landing, we found our CU in the nearest corner of the course and then dropped our landmark. Next, we followed a boundary until we came to a feature which we believed to be part of a mesa, an isolated flat-topped hill with steep sides. We found the ground of the course and the mesa to be completely black. On the moon, this would mean we are in a mare, a large, dark basaltic plain.
Hi, I'm Himanshu Bhushan, and I also focused on network communication for the Winona Lunar Scouts. Periodically throughout this video, we will include maps such as these. The purple X is the landing location of our exploration vehicle and the central unit CU. The purple dotted arrows mark the movement of the EV. The purple circle with the B is the landmark we dropped, and the purple rectangle is our central unit marked CU. Any areas of interest we found will be labeled, such as the mesa and reflective mass. The deep blue lines are course boundaries.
On our way back from the mesa, we found a white feature that resembles a crown. We were uncertain what this object could represent, but it could possibly be a freshwater crater. We also saw some granular substance on the ground. This could be regolith, a blanket of loose heterogeneous superficial deposits covering solid rock.
After locating the paper crown, we lost communication and video feed from our EV. We tried reconnecting, but we were unable. We'd only explored for 1 hour. The purple no symbol is the location of the EV when we lost communication. We blindly attempted to drive closer to the CU, the solid purple arrow, with no luck. We came together as a team and decided we had to make a choice. End the exploration there with not even half a course explored, or have our advisor attempt to restart our rover and risk being disqualified and losing all the work we had put into the project. Unanimously, we had decided. We wanted to test our system more and see if we could make it up the ramp.
We located some other objects of interest after rebooting, but decided to investigate these later in the mission. We made our way up to the ramp and then climbed the mountain to the plateau. On the climb, we found 3 stripes of color, as you can see here on the bottom right. We believe these represent 3 types of basalt found in lunar Maria: very low titanium basalt, low titanium basalt, and high titanium basalt. We also found glittering powder at the top of the plateau, which could be lunar regolith with reflective glass particles.
In this map, the smiley face represents the EV's position when we regained communication. We found the cave entrance, but were worried we would get stuck in the sand.
At the top of the mountain, we found a green bucket symmetrically surrounded by small, smooth glass rocks. The bucket had a white circle and quadratic shape on it, as well as a label. Initially, we could not read the label because it was washed out by light. We were able to use our ability to dim the LEDs to read the label.
We believe the label on the green bucket reads the Sentinel ACC. We carried out research and found a short story named The Sentinel by Arthur C. Clarke, ACC. It's a story of lunar explorers who find a beacon on top of a mountain in Mare Crisium on the moon. We believe this bucket is the beacon, and the stones around it represent pebbles, which when thrown at the Sentinel in the story, slid gently down to the ground.
From the top of the mountain, we spotted a reflective mass, as seen in this picture on the left. In post-processing, we also realized that we saw this mass on top of the mesa from the ground, as you can see in the top right image. In 1969, the Soviets sent a robot named Luna 15 to the moon, which crashed into the side of a mountain in Mare Crisium. We believe the reflective mass could represent this robot or other remnants of past missions. These findings bring us to believe this mystery region we're exploring could be located in Mare Crisium.
On top of the plateau, we found another piece of paper as seen in this image on the left. During the drive-off, we thought we saw a spike in our thermal IR camera readings when scanning it. Because of this, we thought the paper could represent a lunar thermal vent. In post-analysis, we found the thermal spike was only the heat of our LiDAR sensor.
At this point, we had already explored the course for about 3 hours. The team was unable to commit more time than this to the exploration and decided to plot our course for the sand cave. We approached the cave with the knowledge we may get stuck, and sure enough, we did. The sand cave could represent a lava tube with a thick layer of regolith blanketing the ground. Although we ended the course by getting stuck in the sand, we were left feeling proud that our system had lasted beyond the 3-hour operating time we had originally shot for.
This is our final map showing all the area we explored. We had a total of 2 faults represented by the no symbols. The first, as mentioned earlier, occurred when we lost communication with our EV and our advisor had to power cycle it. The second occurred on our way down the ramp. We slid and went outside the boundary.
We were able to perform and analyze 8 different LiDAR scans. The 2 most notable were scan 3, shown in the top right, and scan 6, shown in the bottom right. Both of these scans were rotated to align with the map. The placement of these scans is labeled on the map. We were able to interpret that the corner of the mesa was approximately 60 centimeters or 2 feet from the cliff of the plateau nearby, as shown. We were also able to estimate the width of the front of the course, which we believe to be about 3 to 4 meters or 9 to 12 feet in width.
We learned many, many lessons during this challenge. Here is just a short list of a few of those, including the importance of emphasizing code earlier in the competition. We focused mainly on the hardware development and the video stream instead of home-based visualization and data acquisition error handling. We also did not perform any data analysis on any of our mock trials, which would have made post-mission analysis so much easier and allowed us to find flaws in things like data formatting. We would have liked to take a more action-driven approach early in the competition as well. For example, we could take 4 weeks and do a rough EV prototype and test its flaws and strengths and then repeat that process, adding more functionality to each iteration. Instead, we spent a lot of time just doing research instead of focusing on action. We dealt with the problems we ran into as we went and never performed a risk assessment. Because of this, we did not have a method for reestablishing connection with our EV in the event of a system malfunction like we experienced during mission day. Lastly, we did not prioritize the known lag issue in our video stream. Because of this, we traversed the course very slowly and briefly lost control going down that ramp, which was our second fault.
We would like to thank Adam Beardsley, our faculty advisor. We would also like to thank Thelma, James, Gabe, and the Minnesota Space Grant Consortium for providing us with this opportunity.